Welcome to ScienceCover.com. In this session, we'll look at moments and levers. The aims of the session are to know the parts of a lever, to calculate the moment or turning force, to work with clockwise and anti-clockwise moments, and to perform calculations in situations that are in equilibrium. Before we begin, pause the video and complete the Do Now task. Let's check our answers. You can see the correct answers to the crossword on the screen now. Let's now investigate levers and how they can create a turning force. A lever is a system where a force will cause an object to turn around a pivot point. A lever system is made up from three parts. We have a load, a pivot, and an effort or force. This diagram shows a plank balancing on a pivot. Any object that we are trying to lift is called the load. And to do this, we need to apply a force on the opposite side of the pivot. We call this the effort. Now, if the distance between the load and the pivot is larger than the distance between the effort and the pivot, then the force produced will be larger than the effort force that was applied. Now, it's for this reason that this system is known as a force multiplier, because the force it's creating is larger than the force being applied. Let's look at some simple examples of a lever system. In our first picture, we can see a wheelbarrow. The pivot point is at the wheel. The load is the weight that is being lifted, and the effort is the force being produced by the man. In the second picture, we can see a scissors. The pivot point is the pin connecting the two halves. The load is the mass of the scissors that is being moved, and the effort will be applied at the handles. Pause the video and attempt task 1. Let's check the answers to task 1. What are the three parts of the lever system? We have the effort, the load, and the pivot. Write the names from question 1 in the table to describe the role for each part. So the weight that is being moved by a force, that is the load. The point which the lever is turning around is the pivot, and the force applied to move the lever is known as the effort. Label the effort, load, and pivot on the diagrams. For the wheelbarrow, the pivot is at the wheel, the load is the weight being lifted, and the effort is being produced by the man. For the scissors, the pivot point is at the pin, the load is the blade of the scissors being moved, and the effort is placed at the handle. Now let's look at how we can calculate a moment or turning force. A moment is a turning force around an object or pivot point. Here we can see a spanner undoing a nut. By applying an effort or force to the spanner, we will create a turning force. This will cause both the spanner and nut to rotate. The size of this turning force depends on the size of the effort force and its distance from the pivot point. Now this means that by pushing the spanner with the same size force at different points, we can create different size turning forces. The size of a moment or turning force can be calculated by multiplying the force by the perpendicular distance from the pivot. So in this example, we can see that a force of 2 newtons is being applied to the spanner, and that is a distance from 0.3 meters away from the pivot point. So to calculate the turning force, the moment, we must take the force and multiply it by the distance from the pivot. So this is 2 multiplied by 0.3, which equals 0.6. Now the units for a moment are a combination of the units of force and distance, so that's Newton meters. In this example, we have the same size force, 2 newtons, however we've moved it closer to the pivot point. So to calculate the turning force now, we take the force and multiply it by the distance from the pivot. So that's 2 multiplied by 0.2, and that equals 0.4 Newton meters. So as the force is being applied closer to the pivot, the turning force is lower. Now this means that if the force is applied further from the pivot, then the turning force is larger. Pause the video and complete task 2. Let's check the answers for task 2. Calculate the turning force from each of the following wrenches. A moment equals the force times the distance from the pivot. So for the first one, we have 5 multiplied by 0.3, so that's 1.5 Newton meters. For the second one, we have 3 multiplied by 0.1, so that's 0.3 Newton meters. For the third one, we have 10 multiplied by 0.4, so that's 4 Newton meters. And for the fourth one, we have 15 times 0.5, so that's 7.5 Newton meters. Explain how applying a force at different distances from the pivot will affect the size of the moment produced. So the further away from the pivot the force is applied, the larger the moment created. Now let's look at how we can work with clockwise and anti-clockwise moments. Some situations involve moments that act against each other. We can work out what will happen in the situation by calculating the clockwise moments and the anti-clockwise moments separately. Here we can see 2 children, child A and child B, on a seesaw. So to work out the total anti-clockwise moment, we look at child A. They have a 50 Newton weight and they are 2 meters from the pivot. So the total anti-clockwise moment is equal to the force multiplied by the distance. That's 50 multiplied by 2, which is 100 Newton meters. And the child on the opposite side is applying a clockwise moment. So here we have a force of 30 newtons, and we're multiplying it by a distance of 2. So the total moment in the clockwise direction is 60 Newton meters. Now to work out the overall moment, all we need to do is to take one from the other. So if we take 100 Newton meters and take away 60 Newton meters, we're left with 40 Newton meters in the anti-clockwise direction. In this situation, child B has moved further from the central pivot, so we can work out the total anti-clockwise moment by again taking the force and multiplying it by the distance. This time we've got 50 multiplied by 2 is 100 Newton meters. And child B is now 4 meters away and has a 30 Newton force, so we do 30 multiplied by 4 is 120. Now again, what we're looking for is the difference between the two moments. So I can take the 120 and take away 100, and that leaves me 20 Newton meters in the clockwise direction. In this situation, we have two children on the anti-clockwise moment and one child on the clockwise moment. So to work out the total anti-clockwise moment, we have to work out the moment of child A and add it to the moment of child B. So the moment of child A is 50 times 2, which is 100 Newton meters. And the moment from child B is 50 times 1, which is 50 Newton meters. So the total anti-clockwise moment is these two numbers added together, so that's 150 Newton meters. Now on the opposite side of the seesaw we have child C, who's creating a clockwise moment. So we take their weight, 30 newtons, and multiply it by the distance from the pivot, 4 meters, to get 120 Newton meters. Now the difference between these numbers is 150 minus 120, so that gives me 30 Newton meters in the anti-clockwise direction. Pause the video now and complete task 3. Let's check our answers. Part A, calculate the anti-clockwise moment. So we need to do 2 times 70, which is 140 Newton meters. Calculate the clockwise moment. We do 30 times 4 is 120 Newton meters. Which way will the seesaw rotate? Anti-clockwise. Explain how the two children could place the seesaw in a state of equilibrium. That means we perfectly balance it. To do that, child A could move closer to the pivot point. This would decrease the anti-clockwise moment. Or, if it's possible, child B could move further from the pivot point, and this would increase the clockwise moment. Question 2, we have to calculate the anti-clockwise moment. So we do 50 multiplied by 3 and add that to 25 multiplied by 2. So that gives us 150 plus 50, which gives us 200 Newton meters. Calculate the clockwise moment. We need to do 40 multiplied by 1 and add to that 40 multiplied by 4. So this gives us 40 plus 160, which equals 200 Newton meters. What will happen to the seesaw? And in this case, the seesaw is in what we call equilibrium. That means it's balanced and it's not going to rotate in either direction. Let's now investigate situations of equilibrium in a little more detail. When the clockwise forces equal the anti-clockwise forces, the system is in equilibrium. This means the system is balanced and it does not rotate. In this example, I want to show that the system is in equilibrium. To do that, I need to show that the clockwise moment and the anti-clockwise moments are equal. So to calculate the anti-clockwise moment, I need to do 50 times 4, and that gives me 200 Newton meters. To calculate the clockwise moment, I need to do 40 times 5, and that also gives me 200 Newton meters. So since the clockwise moment is equal to the anti-clockwise moment, this situation is in equilibrium. If we're told that a system is in equilibrium, then we can calculate missing values. In this example, we're told that the seesaw is in equilibrium, and we're asked to calculate the missing mass for person B. Knowing that the system is in equilibrium, we know that the anti-clockwise moment must be equal to the clockwise moment. This means that the force or weight of person A, multiplied by the distance from the pivot, has to be equal to the force or weight of person B, multiplied by their distance from the pivot. If we substitute in the values we're given in the question, this means that 70 times by 3 must be equal to the weight or force of person B multiplied by 7. So 210 is equal to 7F. So to find F, we can divide 210 by 7, and this gives us 30 newtons. And this must be the weight of person B. In this example, we have 3 people on a seesaw, and this seesaw is in equilibrium. How far away is person C from the pivot point? So if it's in equilibrium, we know the anti-clockwise moment must be equal to the clockwise moment. This means that the force times the distance from the pivot of person A plus the force times the distance from the pivot from person B must be equal to the force times the distance from the pivot from person C. So 30 times 4 plus 30 times 1 must equal 50 times the distance from the pivot. So we can write this as 120 plus 30 equals 50D. Now to find D, or the distance from the pivot, we can now take our 150 and divide it by 50. This gives us 3 meters. Pause the video and attempt task 4. Let's check our answers. Number 1. What does equilibrium mean? It means that the total anticlockwise moments equal the total clockwise moments. The diagram shows 2 children on a seesaw. The seesaw is in equilibrium. What is the weight of child B? So the anticlockwise moment must be equal to the clockwise moment. So this means that 60 multiplied by 2 must equal 3 times F. So 120 divided by 3 equals F. And this gives us 40 newtons. Child C sits on the seesaw as shown. Calculate the moment created by child C. So they're 40 newtons and 1 meter from the pivot. So that's 40 multiplied by 1, so it's 40 Newton meters. How far from the pivot would child B have to sit to return the seesaw to equilibrium? So in equilibrium, the anti-clockwise moment must be equal to the clockwise moment. So that means that the force of child A multiplied by its distance from the pivot, added to the force of child C multiplied by the distance from the pivot, must be equal to the force of child B multiplied by the distance of the pivot. So that's 60 times 2 plus 40 times 1 being equal to 40 times D. So this gives us 120 plus 40 equals 40D. So 160 must be equal to 40d. So to find d, I can do 160 divided by 40. This gives me 4 meters.